Electrical safety in the workplace is paramount, encompassing circuit labeling, ground and conductor marking, and ground fault circuit interrupters, or GFCIs. Let's explore each of these critical areas. Firstly, circuit labeling. Circuits must be clearly labeled to identify their purpose and destination. This is essential for several reasons. Proper maintenance and troubleshooting can only occur when circuits are correctly labeled. Accidental energization of circuits can be prevented with clear labeling. Electrical work can be coordinated safely, preventing hazardous situations. Secondly, grounding. Equipment must be properly grounded to protect workers from electrical shock. Grounding provides a safe path for electrical current to flow to the ground, preventing it from traveling through a worker's body. The main components of a grounding system are the grounding electrode, such as a metal rod, plate, or grid buried in the ground, the grounding conductor, such as a wire or metal conduit which connects the equipment to the grounding electrode, and the equipment grounding terminal, such as a screw or clamp on the equipment that connects it to the grounding conductor. Thirdly, conductor marking. Conductors, or wires, must be color-coded or marked to indicate their function. This provides quick and accurate identification of conductors. It helps prevent confusion and reduces electrical hazards. It ensures compliance with electrical codes. Fourthly, ground fault circuit interrupters, or GFCIs. GFCIs are devices that protect workers from ground faults, which can occur when electrical current flows unintentionally through the ground. GFCIs continuously monitor the electrical current flowing in a circuit. If a ground fault occurs, the GFCI will quickly interrupt the current to prevent shock. GFCIs are required in certain locations. These include bathrooms, kitchens, outdoor areas, and construction sites. Employers are responsible for ensuring compliance with Occupational Safety and Health Administration, or OSHA, standards. Regular inspections should be conducted to identify and correct any electrical hazards. These include improper circuit labeling, inadequate grounding, misidentified conductors, and a lack of GFCIs where required. It is also recommended to provide training to employees on electrical safety, including circuit labeling, grounding, conductor marking, and GFCIs. Use written procedures or checklists for electrical work to ensure consistency and accuracy. Establish a lockout-tagout program to prevent unauthorized access to energized circuits. Install surge protectors to protect equipment from voltage spikes. Have an emergency plan in place to respond to electrical accident. Additional topics can include surge protection. Surge protectors safeguard equipment against voltage spikes, preventing damage and downtime. Emergency response plans are critical. Comprehensive plans ensure swift and effective action in the event of electrical accidents, minimizing injuries and property damage. Now let's dive into some electrical grounding practices. Grounding ensures a low impedance path for fault current to return to the source, which facilitates the quick operation of overcurrent protective devices like circuit breakers or fuses. Without proper grounding, fault current may find unintended paths, such as through a person, leading to electrical shock. The grounding electrode system typically includes a ground rod, a metal water pipe, or a concrete-encased electrode, often referred to as a UFO ground. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the electrical panel. Equipment grounding conductors provide a path for fault current from the equipment back to the panel. These conductors are typically green or bare copper. Bonding is also critical. Bonding ensures that all metallic parts of an electrical system are at the same electrical potential. This eliminates voltage differences that could cause electrical shock. Bonding jumpers are used to connect metallic components such as conduit, enclosures, and equipment frames. Now let's look at circuit breaker panel schedules and what goes into the circuit labeling, beyond just lights or outlets. Circuit breaker panel schedule should accurately reflect the loads served by each circuit breaker. Each circuit should be clearly labeled with a description of the area or equipment it serves. For example, kitchen refrigerator, living room outlets, or HVAC unit. Using detailed labels helps in quickly identifying the correct circuit during maintenance or troubleshooting. It also reduces the risk of accidentally de-energizing the wrong circuit. Regularly updating the panel schedule ensures its accuracy over time, especially after any electrical modifications or additions. Another point for consideration is conductor identification. Color coding of conductors is essential for safety and ease of maintenance. In North America, the standard color code is black for hot conductors, white for neutral conductors, and green or bare copper for grounding conductors. Three-phase systems use different colors for each phase, such as black, red, and blue. Proper color coding helps electricians quickly identify the function of each conductor, reducing the risk of electrical shock or miswiring. When working with existing wiring, it's important to verify the conductor identification using a multimeter before performing any work. Now let's talk more about ground fault circuit interrupters or GFCIs. GFCIs are designed to protect people from electrical shock by detecting ground faults. A ground fault occurs when current leaks from a hot conductor to ground. GFCIs work by monitoring the current flowing in the hot and neutral conductors. If there is a difference of 5 milliamps or more, the GFCI will trip, interrupting the circuit within milliseconds. GFCIs are required in locations where there is a high risk of electric shock, such as bathrooms, kitchens, outdoor areas, and construction sites. There are two main types of GFCIs: receptacle type GFCIs, which replace standard outlets, and circuit breaker type GFCIs, which are installed in the electrical panel. Regular testing of GFCIs is essential to ensure they are functioning properly. This can be done by pressing the test button on the GFCI and verifying that it trips. Now for some electrical inspection procedures. Regular electrical inspections are essential for identifying and correcting potential hazards. Inspections should be conducted by qualified electricians or electrical inspectors. The inspection should include a visual examination of all electrical components, including wiring, outlets, switches, and panels. The inspector should look for signs of damage, such as frayed wiring, cracked outlets, or loose connections. Testing of electrical systems should also be performed, including voltage testing, continuity testing, and ground impedance testing. Any identified hazards should be promptly corrected to prevent electrical accidents. Documentation of inspection findings and corrective actions is important for maintaining a safe electrical system. Let's consider some lockout-tagout procedures. Lockout-tagout or LOTO is a safety procedure used to prevent accidental energization of equipment during maintenance or repair. The procedure involves disconnecting the equipment from its energy source and applying a lock and tag to the energy isolating device. The lock prevents the energy isolating device from being turned on, and the tag provides information about who performed the lockout and why. Lockout-tagout procedures are essential for protecting workers from electrical shock and other hazards associated with energized equipment. Training on lockout-tagout procedures is required for all employees who work on or around energized equipment. Now let's look at surge protection devices. Surge protection devices, or SPD, are designed to protect electrical equipment from voltage spikes caused by lightning strikes or power surges. SPD work by diverting excess voltage to ground, preventing it from reaching sensitive electronic equipment. SPD are available in a variety of types, including whole-house surge protectors, which are installed at the electrical panel, and point-of-view surge protectors, which plug into outlets. The selection of the appropriate SPD depends on the type of equipment being protected and the level of surge protection required. Installation of SPD should be performed by a qualified electrician. An emergency action plan is a written document that outlines the procedures to be followed in the event of an electrical accident. The plan should include procedures for reporting electrical emergencies, evacuating the area, and providing first aid to injured workers. Emergency contact information should be readily available, including phone numbers for emergency services, medical facilities, and key personnel. Training on the emergency action plan should be provided to all employees. Regular drills should be conducted to ensure that employees are familiar with the procedures. For electrical safety training programs, comprehensive training programs are essential for ensuring that employees understand electrical hazards and how to prevent them. Training programs should cover topics such as circuit labeling, grounding, conductor marking, GFCIs, lockout-tagout, and emergency procedures. Training should be provided to all employees who work on or around electrical equipment. Refresher training should be conducted periodically to reinforce safe work practices. Training programs should be tailored to the specific needs of the workplace. When looking at electrical safety audits, regular audits are essential for identifying and correcting potential electrical hazards. Audits should be conducted by qualified personnel, such as certified safety professionals or electrical engineers. The audit should include a review of electrical safety policies and procedures, a visual inspection of electrical equipment, and testing of electrical systems. Findings from the audit should be documented and used to develop corrective action plans. Follow-up audits should be conducted to ensure that corrective actions have been implemented effectively. Now let's discuss electrical safe work practices. Safe work practices are essential for preventing electrical accidents. These practices include energizing equipment before working on it, using insulated tools, wearing personal protective equipment or PPE, and maintaining a safe working distance from energized equipment. Working on energized equipment should only be performed when energizing is not feasible, and only by qualified personnel using appropriate safety procedures. Regular training and reinforcement of safe work practices are essential for maintaining a safe work environment. Let's talk more about PPE. Personal protective equipment, or PPE, is essential for protecting workers from electrical hazards. PPE includes items such as insulated gloves, safety glasses, arc flash suits, and insulated footwear. The type of PPE required depends on the specific electrical hazards present in the work environment. PPE should be inspected regularly for damage and replaced as needed. Training on the proper use and care of PPE is essential for ensuring its effectiveness. Now let's consider electrical hazard analysis. A hazard analysis is a systematic process for identifying and evaluating potential electrical hazards in the workplace. The analysis should consider factors such as the type of electrical equipment being used, the work environment, and the training and experience of the workers. The results of the hazard analysis should be used to develop control measures to eliminate or minimize the identified hazards. Control measures may include engineering controls, administrative controls, and the use of personal protective equipment. Regular review and update of the hazard analysis are essential for maintaining a safe work environment. For arc flash protection, arc flash is a dangerous phenomenon that can occur when electrical equipment is subjected to a short circuit. The resulting arc flash can produce intense heat, pressure waves, and flying debris, which can cause serious injuries or even death. Arc flash protection measures include conducting an arc flash hazard analysis, implementing appropriate engineering controls, using personal protective equipment, and providing training to workers. Arc flash studies are used to determine the level of arc flash hazard and to select appropriate protective measures. Now for grounding electrode testing. Regular testing of grounding electrodes is essential for ensuring that the grounding system is functioning properly. The testing should be performed using a ground resistance tester, which measures the resistance of the grounding electrode to earth. The measured resistance should be within acceptable limits, as specified by applicable standards and regulations. If the resistance is too high, the grounding electrode may need to be replaced or supplemented with additional electrodes. Documentation of testing results is important for maintaining a safe electrical system. Now let's discuss electrical system maintenance. Regular maintenance of electrical systems is essential for preventing electrical accidents and ensuring reliable operation. Maintenance activities include inspecting electrical equipment for damage, tightening connections, cleaning equipment, and testing protective devices. Maintenance should be performed by qualified personnel using appropriate safety procedures. A preventive maintenance program should be established to ensure that maintenance activities are performed on a regular basis. Documentation of maintenance activities is important for tracking the condition of electrical equipment and identifying potential problems. Now for electrical safety compliance. Compliance with electrical safety standards and regulations is essential for protecting workers from electrical hazards. Applicable standards and regulations include the National Electrical Code or NEC, OSHA regulations, and state and local electrical codes. Employers are responsible for ensuring that their electrical systems and work practices comply with these standards and regulations. Regular audits and inspections can help to identify and correct any compliance issues. Now let's talk about the National Electrical Code, often referred to as the NEC. The NEC provides comprehensive guidelines for safe electrical installations. It covers topics such as wiring methods, overcurrent protection, grounding, and equipment installation. Compliance with the NEC is essential for ensuring the safety of electrical systems. The NEC is updated every 3 years to reflect changes in technology and best practices. Now more about OSHA. OSHA is responsible for enforcing workplace safety standards, including electrical safety standards. OSHA conducts inspections of workplaces to identify and correct hazards. Employers who violate OSHA standards may be subject to fines and other penalties. OSHA also provides training and resources to help employers comply with electrical safety standards. For electrical safety resources, there are many resources available to help employers and employees improve electrical safety in the workplace. These resources include publications, training materials, and websites provided by organizations such as OSHA, the National Fire Protection Association, or NFPA, and the Electrical Safety Foundation International, or ESFI. These resources can provide valuable information on electrical hazards, safe work practices, and compliance with electrical safety standards. Now some further discussion on GFCI protection in specific locations. GFCIs are specifically required in areas where electrical equipment is likely to come into contact with water, increasing the risk of electrical shock. These locations typically include bathrooms, kitchens, laundry areas, and outdoor locations. The NEC specifies the specific requirements for GFCI protection in these areas. GFCIs should be installed in accordance with the manufacturer's instructions and tested regularly to ensure they are functioning properly. Now let's talk about arc flash hazard analysis in detail. An arc flash hazard analysis is a systematic process for determining the potential arc flash hazards in an electrical system. The analysis typically involves collecting data on the electrical system, performing calculations to determine the incident energy levels, and developing recommendations for arc flash protection. The results of the arc flash hazard analysis are used to determine the appropriate level of personal protective equipment or PPE required for workers who may be exposed to arc flash hazards. Arc flash hazard analysis should be performed by qualified personnel using appropriate software and tools. Further, arc flash boundary determination is important. Arc flash boundaries are established to define the areas around electrical equipment where workers may be exposed to arc flash hazards. The arc flash boundary is the distance from the electrical equipment where the incident energy level is equal to 1.2 calories per square centimeter, which is the threshold for a second-degree burn. Workers who enter the arc flash boundary are required to wear appropriate personal protective equipment or PPE. Arc flash boundaries should be clearly marked to warn workers of the potential hazard. More discussion on PPE selection for electrical work. The selection of appropriate PPE for electrical work depends on the specific hazards present in the work environment. Factors to consider when selecting PPE include the voltage level, the potential for arc flash, and the potential for electric shock. PPE should be selected in accordance with applicable standards and regulations such as National Fire Protection Association or NFPA 70. Training on the proper use and care of PPE is essential for ensuring its effectiveness. Let's talk about electrical safety for qualified persons versus unqualified persons. Qualified persons are those who have the skills and knowledge to perform electrical work safely. Unqualified persons are those who do not have the skills and knowledge to perform electrical work safely. Only qualified persons should perform electrical work on energized equipment. Unqualified persons should be kept away from energized equipment and should not attempt to perform any electrical work. Employers are responsible for ensuring that only qualified persons are allowed to perform electrical work. Additional training on the use of voltage testers is helpful. Voltage testers are used to verify that electrical equipment is energized before work is performed. Voltage testers should be used in accordance with the manufacturer's instructions. Voltage testers should be tested before and after each use to ensure that they are functioning properly. Workers should be trained on the proper use of voltage testers. More on the importance of maintaining electrical safety records. Maintaining accurate electrical safety records is essential for demonstrating compliance with electrical safety standards and regulations. Electrical safety records may include documentation of electrical inspections, maintenance activities, training programs, and hazard analyses. These records should be kept organized and readily available for review by regulatory agencies or other interested parties. Electrical safety records can also be used to track the performance of electrical systems and identify potential problems. Finally, let's touch on electrical contractor safety requirements. Electrical contractors are responsible for ensuring the safety of their employees and the public when performing electrical work. Electrical contractors should have a written safety program that includes policies and procedures for electrical safety. Electrical contractors should provide training to their employees on electrical safety. Electrical contractors should ensure that their employees are using appropriate personal protective equipment or PPE. Electrical contractors should comply with all applicable electrical safety standards and regulations.